what I tried to do was I did there exists and then X is a farmer implies, but I caught myself
No,
and
no,
I
yeah.
remembered it's and.
It's and. It can't be implies. There exists there exists X, f of X implies is simply true no matter what follows. So this statement, I mean, I don't care how outlandish what you say here. Okay, this statement is true. So maybe let me not write that. Just whatever outlandish statement you want to put here. This is automatically true. Right? Let X be a non-farmer. Let X be a non-farmer. That non-farmer in the universe makes this false, and then the implication is true for at least one thing in the universe. Okay? Existentialist quantification always goes with conjunction. Existential quantification in your subject always goes with conjunction. Universal quantification in your subject always goes with implication, and never the other way around. Okay, so there's no confusion, no ambiguity on this issue. Okay, there's two different quantifiers that one can use. Right? Implication and conjunction in these two types of quantification, and you can't interchange them. One quantification goes with one connector, the other quantification goes with the other, and never the other way around. And so it couldn't be less ambiguous. You may be wondering what about disjunction? Well, disjunction is implication in another form. Okay, so that goes with universal. Right. What else? What else? You had a couple questions. 1E.
The other one I had, I was having trouble on two. The first couple at the top there.
Okay. So for every x and for every y, x plus y is greater than x. Well, let's start it off. How about here? X plus y is strictly greater than x for every x and every y. Folks, what do you think? X plus y is strictly greater than than x for every x, or for every x and y. Excuse me.
Would it be false?
That would be false. What's the problem?
False, yeah.
What's the problem?
It's all x's and all y's.
But I mean, why does it fail? Which y's does it fail for? Which x's and y's? When does it fail? That x plus y is not greater than x.
The negatives?
No negatives here. No negatives over this domain. Yeah, in these domains, sure. When x and y are negative, well, When y is negative, x plus y is definitely not bigger than x. What about here? Is it true here? X plus y is bigger than x? I said no. Go upstairs. Come on, guys. In this domain, x plus y is bigger than x. Is that always true? That x plus y is bigger than x?
You could do like 3 plus -3.
This domain here. No -3 in this domain.
Which domain are you going to?
The middle one, do you see my cursor?
No,
Oh, okay. Well,
that may add a little confusion.
yeah, sorry. So here, do you see this, what I've highlighted?
Yeah.
Okay. Well, what if x and y are equal?
It's fine. Still bigger than x. 3 plus 3 is still...
Right, it is.
You could do 5 plus 0.
Right, so the z with the 0. Okay.
Oh, okay.
Right. So it's false all the way around there. Okay. False in every domain there. It's almost true in the second domain. What could I do to the second domain to make it true?
Remove 0.
Yeah, if you remove the 0, then it would be true, but 0's there, so it's just not true. So now in the second statement here, for every x, there exists a y such that x plus y is less than x. That's going to require y making x smaller, right? And again, it's not every y, it's some y. So it's existentially quantified rather than universally quantified, the y. Okay? So for example, over this domain, it's true. Just make y negative. I'm sorry, I guess you can't see. Over this domain, the second statement is true. Just make the y negative. As a matter of fact, that's what you need to happen. The y needs to be negative, which can happen over this domain, but not this domain. Is that clear?
So you kind of have to look for instances where it's false in some ways.
For universally quantified statements, all you need is one time where it's false to say the statement is false. So for the first one, that's a universally quantified statement for x and y. Second statement is universal for x, existential for y. So to show that one goes wrong, you need that every y will not satisfy this. Every y doesn't satisfy that.
So then when we're looking at there exists an x for every y, like x plus y equals 0, we're looking for one x that satisfies any y at all, like one singular x.
Right.
Okay.
And we covered that one as an example before, and it's essentially false. That one, it's essentially false everywhere, except over the domain that is just 0 by itself. The domain that contains just 0, that's true. If the domain contains anything more than that, it's false. Because the y, the x that adds to y to go to be equal to 0, depends on what y is. If y is 5, then x is negative 5. If y is 6, negative 6, then x is 6. Right? If y is 0, then x is 0. Then it's the only time they match up. But right here, for every x, there exists a y such that x plus y is 0. Well, that's true here. That's true over the first domain. For every x, there exists y that is the negative of x in the domain, and they add to 0. What about in the second domain here?
No.
No. You don't have negatives. What about in the third domain? Do you always have the negative of every number?
No.
No.
No, just the 3.
Not a 3.
Yeah, not the 3. So that's enough to ruin it, because it's got to be for every x. All right. What else? What else? All right. It's fairly clear we haven't started the assignment yet, really. I haven't gone through the majority of it. So, please get started on it, and let's have some questions on Wednesday. We got to get things moving. We can't dawdle too much. We got a lot to get through in the course. Okay. So it's not going to happen for you if you try to do it all the day before. Okay, trust me. This is a course that's meant to sort of open your mind a little bit. So it takes time for things to sink in, so to speak. It's not like in calculus, right, where there's a 12-year build-up, 13-year build-up to taking calculus, and all the concepts should be familiar to you. No, here it's a lot of new stuff thrown at you at once. Okay, unfortunately, school curriculum in mathematics is simply geared towards taking calculus and not much else. All right, so please get started on that, and we'll take more questions next time. Of course, you can always email me your questions. We can meet sometime if you need to meet. We can meet together. All right, I'm available. All right, so the first exam. So I'll have. So we're going to start on chapter 3 today. So I'll post an assignment for chapter 3 on Wednesday. Now, in chapter 3, we're going to get started on doing formal proofs. Okay, so you're going to need to, keep on top of that material. Okay, so I'll post an assignment for chapter 3 on Wednesday. Exam 1 will cover chapters 1, 2, 3. So tentatively scheduled for Friday the 26th. All right. Exam questions will be much like the homework questions.
I'll probably start that assignment the day it's posted.
Okay, good. And may also be taken directly from examples done in class. So I will often just take examples I did in class and make those the exam questions. Not like for every question, but for some of them, sure. Right? Again, you need to go over the examples that I do on your own without looking at my solution, and then comparing your solution to mine, and correcting your mistakes and looking at it again. All right, that's what needs to be done. All right, it's the learning here is different than learning calculus. All right, so let's get started on chapter 3. So chapter 3 is on it's called naive set theory as opposed to formal set theory. Formal set theory is really just sort of for doing most of mathematics, it's actually not that important, but it's an attempt to put naive set theory on a consistent footing, on a consistent foundation. Logically consistent foundation. Naive set theory is not built on a logically consistent foundation. Because there's these various logical paradoxes that come about, which I'll touch on them as we go forward. However, normally one does not run into them. So for most purposes, naive set theory is just fine, especially if you're just dealing with finite sets. With infinite sets, these paradoxes can crop up. All right, so definition. First problem with naive set theory is that the definition of a set is not really rigorous. It's just sort of an intuitive thing. A set is a collection of objects called elements, presented in no particular order. And we write X, then there's this epsilon symbol here, A, to mean element X is in set, capital A. And then we write X, and then we put a slash through that epsilon there to say element X is not in set A. So, for example, so one can write a set. So sets are usually delimited by this, delimited. By the brace symbol. So left brace and right brace. Okay, so that's the beginning of the set and the end of the set. End of the set. Okay, and the simplest way to express a set is, if possible, just listing out the elements. Keeping in mind that the order so if I write something like this, 4, 8, 7, 3, 9, -2, right, is the set containing 1, 2, 3, 4, 5, 6. 4, 8, 7, 3, 9, and -2. Now, this is the same as the following set. So if I was to take that set and then, maybe juggle some things around, 4, 7, 7, 9, 8, like that, -2. That's the same exact set. There's no inherent ordering to the elements. So you present them in whatever ordering is convenient. This is also the same set. So if I was to perhaps repeat myself, and it may seem silly right now that I'm repeating myself, but it actually isn't, because there's certain ways of describing sets in which you always get repetitions of an element. This is the same set, okay? There's just 6 elements in it, 4, 8, 7, 3, 9, and -2. An element is either in the set or not in the set. It's never in the set more than once. Or not. It isn't in you can have a concept of belonging to, a collection of things more than once. That's called a multi-set, but that's not what we're looking at here. So now, if you look at this set of numbers here that we've defined, you'll notice that 8 is an element. Is an element of this set. However, 16 is not an element of that set. So on and so forth. Sets can contain anything as elements. It doesn't have to be numbers or letters.
Geometric objects.
Sure. Numbers, symbols, geometric objects. And even other sets. So, for example, if I had a 3 triangle, hexagon, and the set square root of 2 pi. This set has 1, 2, 3, 4, 5 elements. Maybe I'll make this one a little bigger. Has 5 elements. They are A and 3 and the triangle and the hexagon and this set here. So this set is one element of this larger set here. It itself is a set with 3 elements in it, but as far as the larger set is concerned, it is just one element within it. So, for example, maybe I'll even make this a little different. Why don't we make this the letter 3 here, or the number 3. So, for example, right, triangle is an element of this set. 3 is an element of this set. 3 is also an element of this set here. But the square root of 2 is not an element of this set. The square root of 2 is not an element of this set. Right? The elements of this set here, delimited by this brace and this brace, there's 5 things. Here's element 1, here's element 2, here's element, again, no particular order, but just how we have them listed here. Here's element 4, and then here is element 5. Right? And element 5 is itself a set, and that set contains within it the element square root of 2, although it is not an element of this outside set. So subtle distinctions, but very important ones. From a standpoint of mathematical logic, from a standpoint of programming languages and computer science, and various other things. So the square root of 2 is an element of this set. Are we seeing the difference? What I'm talking about here? Any questions about that? Right, the number 3 is an element of the set that starts here. It's right there. The number 3 is also an element of this set here. It's right there. The square root of 2, however, is nowhere to be seen in this set. It's got this element, this element, this element, this element, and that. I don't care what that last thing is. It is not the square root of 2. It is a set that has elements, among which is the square root of 2, but it isn't in that bigger set in and of its own right. Well, that's right, I forgot. Our undergraduate program in mathematics, it requires actually 1 semester of computer programming. Has anybody done that yet?
Taking it right now.
Okay. So you'll learn about, like, delimiters and parentheses, nested parentheses, and I mean, depending on what language it is, it takes different forms, but, getting those nested parentheses in the right place and in the right order, I mean, it makes all the difference in the world as to whether your program is going to work or not. You can't tell the computer, "Oh, that's not what I meant, really. I meant this," right? I mean, the computer doesn't know. All right. So now this brings us to Russell's paradox. Since sets can be elements of other sets. Oh, before we get to Russell's paradox, sorry. So that's the easiest way to sort of describe a set as just, well, here are the elements of the set. And we just do it like that. But you can't always do it that way. I mean, especially when you've got infinitely many elements, it becomes more and more difficult to just list them out in some way. You can do it with infinite sets. I mean, we've been doing it already. When I write 1, 2, 3, 4, 5, 6, like this, ... I mean, y'all know what I'm talking about. I'm talking about the positive integers from 1 to 6 to 12 to, 2 bazillion and 12, so on and so forth. Right, so, but not all infinite sets are quite so easy to describe. So another way to describe sets is with set builder notation. So when we write this, what it means is the following. So this is the set, this symbol is red, the set of all elements x, and then this vertical line is red such that, and then this is p of x, the predicate. The set of all elements x such that p of x is true. All right. Sometimes it's written like this. As the set of all elements x, and then the such that is made a colon. P of x is true. When you're writing things by hand, typically this is used. When you're doing things in typeset, this is used. On a typesetting program, the colon is used more so than the vertical line. But either or. I'll do that later. So, for example, so the natural numbers is the set, I don't know why I capitalized that. Natural numbers is the set the positive integers and 0. And it's written like this. So you just make a capital N like that, and then just drop another line down like that. And so that's the set of natural numbers. So now the set of integers is therefore, so you make you make half the z like that, and then you double up there. See how I did that? So instead of making a z like this, you do it in 2 steps. Make this angle, and then make that angle, sort of doubling it up like that. It's the set of all x and minus x such that x is an element of the natural numbers. So it's a set of all elements, and you can have like more than one symbol here. The set of all elements x and negative x, such that x is in the natural numbers. So all the positive and negative whole numbers. That's one way to write it, with set builder notation. Why the z? Z is a German word. It stands for, I think it's Zahlen or something like that. I wouldn't know.
Zahlen.
Zahlen, yeah, I wouldn't know. The set of rational numbers. What's the set of rational numbers?
A over B.
Mm-hmm. So rational numbers symbolized by Q for quotients. It's the set of all A over B such that, what are A and B? Anything? Not anything.
Integers.
Integers, right? So such that A is an integer, and
B's not equal to 0, right?
B is an integer, right? And B is not 0. So now this thing about listing an element more than once appears, because when you're talking about the rational numbers, A over B can be the same as C over D, right? I mean, 5 over 10 is the same as 1/2. It's a different pair of integers, right? But it's a different pair of integers, but it's the same rational number. So rational numbers get listed more than once, and as a matter of fact, they get listed infinitely many times. Okay? So some examples of rational numbers. Right, 0, which is equal to 0 over whatever, 0 over 1. Any integer, 5 over 1, 3/2, which is the same as 9/4. No, it's not the same as 9/4. It's the same as 6/4. Minus 3/2, which is the same as 3 over minus 2, which is the same as 6 over minus 4, etc., etc. Right? Some numbers that aren't rational. Anyone know some numbers that aren't rational?
I.
Oh, sure, I. Yeah, I mean,
Square root 2.
1. That's not even a real
Said pi.
pi. Yeah, pi. Square root of 2. Well, showing that pi is not rational is actually pretty complicated. Showing square root of 2 is not rational is definitely a doable thing, and we'll do that at some point. Not today, but we'll get to that. The nice example of a proof that we'll do later. And then this square root of -1. I mean, that's not even considered to be a quote unquote real number. They call it imaginary, although there's nothing really imaginary about it. It's a perfectly legit number in and of its own right.
Euler's constant.
Euler's constant, E, sure. What makes square root of -1 a legit number? That's a kind of a loaded question. I'll leave you to think about that.
Is there an equation for it?
I mean,
For I?
it's the solution to this. Plus and minus I are the solution to that. And you may think, well, squares can't be negative. Well, squares of real numbers can't be negative. So people don't really use imaginary to say complex numbers can be. And complex numbers, I mean, they work essentially. What makes numbers worthwhile is the fact that they work. We do things with them, and we're very happy with those things that we do. When you look back in history at the development of numbers, they were used to help keep track of, how many bushels of barley you're trading with this guy and how much you got paid back in terms of, of wheat from this guy and so on and so forth. Keeping track of commodities. Right? And then the Egyptians used them for calculating areas, numbers, right? And the Mayans had dates, and they kept track of dates, and that was an important thing for them. And things took shape after that. They work for us in some way. I also works for us in ways that I'm not going to get into, but it works in a lot of really nice ways. That's what makes it legit, as far as I'm concerned. It's just my opinion. All right, so now we come to Russell's paradox. So we have said that sets can be elements of other sets. Right? This leads to paradox. Perhaps you've heard the following. So in a certain village, there's one barber.
Who shaves every barber that doesn't shave himself?
I'm trying to think. Yeah. So in a certain village, let A be the collection of guys who shave themselves. How does it work? I'm forgetting how it goes. Yeah, let A be the collection of guys who shave themselves. Yeah, a guy either shaves himself or he's shaved by the village barber. So let A be the collection of guys who shave themselves, and let B be the collection of guys who are shaved by the barber. So, men who shave themselves. And B is the set of men who the barber shaves. Right, so where's the barber? Does he shave himself? Right, but if he shaves himself, the barber only shaves people who shave themselves. The barber is the man who shaves those who don't shave themselves. So the barber can't shave himself because he only shaves those who don't shave themselves. But he can't be shaved by the barber because then he shaves himself and he wouldn't be here. So that's sort of a verbal logic example of Russell's paradox. But the formal one is this. So let A be equal to the set of all sets, we'll call it X, be the set of all sets B, such that B is an element of B. And let Y be equal to the set of all sets B, such that B is not an element of B. Right? We have said that sets can be elements of other sets, but what about a set that is an element of itself? Either the set B is an element of itself, or B is not an element of itself. Where is the set Y? Is Y an element of itself or not? Is Y an element of X, or Y an element of Y? If Y is an element of Y, then Y is an element of itself. Then by definition, Y is an element of X. Contradiction. If you say that Y is an element of Y, then Y is an element of itself, so Y must be an X. A contradiction. If Y is an element of X, right? If Y is an element of X, then by the definition of X, Y is not an element of itself, right? Or sorry, Y is an element. If Y is an element of X, then by the definition of X, Y is an element of Y. Again, a contradiction. Right, and a set is either an element of itself or it isn't. So it's either in X or it's in Y. But you can't figure out where Y is. This set Y itself, where is it? Is it here in X or is it in Y? If you insist it's in Y, then by the definition of Y, Y is not an element of Y. So I guess we can write it this way. That's a contradiction. So by the definition of y. If you insist that y is an element of x, then by the definition of x, y is an element of y. Again, a contradiction. You can't figure out where it's supposed to be. That's the paradox. So we say that naive set theory isn't logically consistent because it leads us to this problem. And there is this notion of formal set theory which corrects that and puts set theory and thus all of mathematics on a logically consistent foundation. It's way too complicated to really even bother with, but anyway, it's there. For the most part, naive set theory works just fine, as long as you kind of watch out for these kinds of paradoxes. Okay, so that's all for today. So please get started on the assignment, and let's take questions.